Okay, thank you very much. So let's kind of continue where we left off tomorrow, which was kind of the homework food for thought. The requirements for polarimetry for hadron or proton polarimetry at the EIC. And the only thing that we converged on so far was the absolute depolarization, which comes from physics on the order of 1% relative. So the question was, what else do you think you need to consider to meet all your goals based on what we discussed in the hour before that? So one obvious thing is the time dependence polarization decay through your several hour long storage. Then we need to be able to identify the bunch by bunch polarization. The bunches have a transverse and longitudinal dimension size, so we should be able to measure this polarization potential polarization profile of these bunches, and then it would be nice to really map the polarization during the ramp to see what the effect of the strong resonances are when we cross them. And then lastly, but unimportant, is really the direction of the polarization vector at the experiment, because as we saw, some experiments want the polarization direction rotated from vertical to longitudinal, and we really need to make sure that the experiment gets what they want, right? So moving on now to polarimetry of high energy hadron beams. What we're after is this bunch of particles that travels in vacuum and moves at just about the speed of light. So how do we get there? But before we actually talk about getting there, I would like you to look at this picture and give a guess what the polarization of this bunch is. On first order, it looks pretty polarized, right? There's a lot of ups here. There's a down here, down there, and down there. So it's only 4 downs. Looks like it's pretty much polarized. But if you sort this out and calculate the polarization, you have 16 in total minus 4 so 12 up minus 4 divided by the 16. The polarization is actually only 50%, which gives you a little bit of an idea of what you actually try to achieve. If you want to get up to 70%, it means that only 3 out of 20 particles are allowed to have an opposite direction to the preferred one, right? So it's actually much harder than you initially think, because a polarization of 0 really means you have equal up and down spins. Okay, so back to the problem at hand. How do we measure this? And it's a bit of a chicken and egg problem, because we need to somehow probe this bunch and figure out how many particles have an upspin and how many particles have a downspin. So we need to find a way to interact with this bunch, get a representative sample of the particles to measure this polarization. It's essentially an experiment in itself, like we talked about yesterday, only the opposite direction. So we need some sort of analyzing power in our experiment to measure the beam polarization. So how do we get there? Before we continue here, I just want to probably more reiterate and introduce not only a fraction of our scattering probability actually will be spin dependent. So we have an unpolarized contribution here to this cross section, and then the spin dependent. So we're essentially always talking about this asymmetry, which is the normalized difference over the sum, which we just call this small a, or at one point a capital A, the analyzing power that we're after to determine the beam polarization. So before we think about the experiment itself, I want to introduce the right frame, and the right frame really is defined by our scattering plane. So we have this experiment in mind where we have the polarized beam, we have some sort of target, and we do a scattering experiment. So we have a left direction, a right direction, which the scattered particle with the beam momentum, which defines our scattering plane. And then we have the longitudinal direction, which is the beam direction. and the scattering sideways direction and normal to the scattering plane. So that's our frame that we want to talk about. So the sideways is the normal direction across the longitudinal direction, and everything that we do is described in this scattering frame. So if we then have an asymmetry, the scattering particle tends to maybe go more to the left than to the right, we calculate our asymmetry with respect to this normal beam polarization, and that's our asymmetry here, which we describe as the analyzing power AN times the beam polarization. And this AN now really tells you that the experiment has a left-right asymmetry with respect to the normal beam polarization. There could be other beam polarizations. The beam polarization could be longitudinal, that would be an AL, or the beam polarization could be sideways, that would be an AS, but we always talk about the left-right asymmetry in our scattering plane. Now, if we go a step further and maybe limit ourselves to elastic scattering, so we have a beam, that's the proton, obviously, and then we also use a proton target. We have certain conditions that we have to apply, but before we get there, we have this scattering matrix that describes our transition from the initial state to the final state, and we have all sorts of different densities here as combinations of the different beam polarization or target polarizations that we think of. So then the total cross section is the trace of our final state here, which we describe like this with the densities, and we can expand this in terms of these different parameters, where the subscripts here, the first, second, and the fourth, really refer to the scattered particle, the recoil, the beam, and the target polarization states. And then we have these analyzing powers here, these A factors, which have different contributions from the different potential orientations of our beam, target, scatter, and recoil particles or protons in this case. So each of these can point in the normal direction, the sideways direction, the longitudinal direction, or be unpolarized. So it's either 0, N, S, or L, and the total scattering matrix therefore has 256 possible observables for the full experiment. Now we talk about elastic proton-proton scattering, so we have parity, conservation, time invariance, and other symmetries that we should consider and make sure that they're obeyed. So some of these parameters actually are 0. Some of them are the same, might have an opposite sign. So this whole thing for elastic PP scattering boils down to 25 independent parameters. And then the question is, which ones are actually sizable, usable, that we can use this to actually make an experiment to measure an asymmetry for a polarized beam. So, yes.
May I just seek a question of that background there? So, if we collide electron and proton beam, so we define this left-right asymmetry with respect to the proton beam, right?
Well, this whole setup really is only for elastic proton-proton scattering. You can define this more generally, but then your symmetry is going to look different.
I don't know if I understand, because I'm just trying to look at that proton beam.
Yes, this
yeah,
one.
with respect to the transversely polarized beam, right?
Yes.
So I'm looking at the EIC. So if you have electron and proton beam, so which reference point are you looking at? Is it the...
Well, in this case, I'm not specifically looking at the EIC. I'm looking at a particle beam. What I think what you're thinking about is the electron-proton collision in the experiment. that's not my primary goal here. I want to measure the beam polarization of the proton beam, and I'm trying to find a way to do that.
Okay.
Whether there might be a way to do that in your experiment too with the polarized EP collision. But that's probably not the case because you want to make those experiments because you don't really know what's going on there, right? You need to find, this is something that you need to do in order to provide input to your EP collision. All right. There was another question. You're good. Okay. Okay, well, what was I? I introduced all these parameters and variables. I'm going to rewind this because really what we want to talk about is only this AN. And that's essentially this A00N0, which is where the beam is polarized, it hits the target. And we're not interested in any polarization of the final state. We just want to make sure that it's an elastic scattering, right? So then if this beam is polarized and the scattering particle tends to go more to the left than to the right, we can flip this picture around. If the target is polarized and the beam hits it, the target would tend to go more to its left also, right? Because the beam tends to go to this way. So the target would tend to go to that way if it's polarized, which essentially means that the A000N, this analyzing power is exactly the same as the one where the beam is polarized. So we can think of an experiment where we have the polarized beam on an unpolarized target, measure the asymmetry, and we can have a polarized target with an unpolarized beam, and we measure the asymmetry. When we compare those two measured asymmetries, we take the ratio, the asymmetry of the beam divided by the asymmetry of the target should be the same as the beam polarization divided by the target polarization. Well, that's nice. So we can measure two asymmetries and we have two polarizations here. How does that help? Well, it helps in the way that if we measure these two asymmetries and we don't know the beam asymmetry, maybe there's a way we can measure the target asymmetry differently and use it as an input. And that way we essentially determine the beam polarization because we measure this, we know that's the same, and that way we get the beam polarization. So we have identified what's the chicken, what's the egg. We only need one of the two now. So for the experiment itself that we want to do, like I said before, this is all talking about the scattering plane. So it's defined by my scattered and recoiled particle and the beam direction. When I do the experiment, I talk about the lab frame. So I have a detector on this side, a detector on that side, but I somehow have to rotate event by event my scattering plane into my lab frame, and that's really just a rotation around the beam direction, right? This is my lab frame XY, and then this is the scattering planes and sideways normal, and it's just a translation sine phi cos phi that rotates one into the other. Now that being said, my detector has an efficiency. We talked about the luminosity yesterday and how we get from the cross section to our counted events or counted particles, and this would be the homework for discussion for today. If you take this equation and think about how the detector, luminosity, possible time dependence, efficiencies, and luminosity dependence on the different polarization states translate into this, and you plug in essentially the PN rotation into your cos phi here into the lab frame. What possible sources of systematic uncertainties can you think of? And is there a way that you can avoid them, minimize them, or get rid of them? So what I would like you to think about later today is take this, expand this a little bit, think about the detector locations, what the beam polarization direction is, and how you can put this all together to remove systematics. Doesn't I should say this might be an illustration, it might be real data. So what this really means is for an unpolarized measurement in X and Y, you would have a distribution of your events that's just a circle. If you introduce this asymmetry, this polarization dependent left-right asymmetry, it might translate into this light blue circle. And then what you measure might be looking like this red distribution. So the question is how, if this efficiency is smaller than that efficiency, how can you get how can you find a way to mitigate this? So back to my favorite example that we started yesterday, one experiment from this cooler synchrotron storage ring in Germany. That's the previous ETA experiment, which was an experiment that was specifically designed to really measure a lot of those different spin correlation coefficients, those AN parameters for different polarization combinations. And this detector itself was very much optimized to measure elastic proton-proton scattering. So we have this polarized proton beam that goes up to 3.3 GeV in momentum, and then we have a fixed target here. And we have the scattered proton and the recoiled proton. And this detector essentially was just a simple scintillator hodoscope that was specifically laid out to measure two particles and the kinematic correlation between those two. Kinematic correlation for elastic scattering obviously means that in the azimuthal direction, the two particles are back to back. So there's 180 degrees between them. And then you have this kinematic correlation in the polar angle, which at low energy really means that there's a 90-degree angle between the two particles, right? So if you talk about very high energies, the scatter particle would go very forward and the recoil would go pretty much sideways. If you have higher momentum transfer, the scatter particle would go this way, but there's a 90-degree angle between the two. So now we're back to finding a target here that's, first of all, thin, because this is a storage ring. So we don't want to just lose the beam in just one interaction with the target. But also importantly, since this detector is really optimized to measure this back-to-back correlation of the two particles, you really only want two particles in your detector, right? You don't want much background pile up or multiple events in your interaction. So you want a thin target here where the interaction probability is fairly small, so you can really nicely identify the elastic scattering events. And the way to do this is this atomic hydrogen target, and now your alarm bell should ring because that's what we talked half of yesterday's lecture. How we actually devise a polarized proton beam or target in this case. And this is really exactly the same what we went through yesterday. We have this setup where we try to separate the four hyperfine states, and then we sort out one half of them. We have an RF transition, and then we sort out the other one, and we have the polarized proton nucleus and the hydrogen. So we have the essentially an H2 bottle here that's dissociated, cooled nozzle to have a nicely focused beam. And then we have a magnet here that does step one. We have the RF transition that does step two. And then we have another magnet that does step three. And we have a nicely polarized proton in here. And then all we need in the interaction region is a magnetic holding field that allows us to define the direction of our polarized target. And on the other side, what we now do is we essentially do the same, where we again sort out the states that we're not interested in, and we see how much actually survives of this. That's called a Rabi unit, and we can use that to measure the target polarization. So we can switch we can switch this off, measure the particle flux. We can use different combinations of these here, measure the particle flux, and when we compare this, we really can measure the target polarization external of our interaction. So that's step 2, right? And we're done. The target polarization here is 70%. We use that as input when we compare our beam asymmetries with the target asymmetries, and we're good to go. And before we actually use this, a few words about formalism for people who like this. This is nicely described in this Coulomb nuclear interference region. That's essentially a formal description where we have the where we describe the observables in terms of these spin flip amplitudes, and it turns out that the single spin asymmetry AN, this normal asymmetry, is essentially an interference of the electromagnetic amplitudes with the hadronic amplitudes of these two. One is a single spin flip amplitude, and the other one is the no spin flip amplitude. It's a combination of these two that interfere. So these are no flip amplitudes. If you look at the initial and the final states here, and this is a single spin flip amplitude, and the electromagnetic and hadronic amplitudes interfere in this region such that this analyzing power actually is the largest. And the largest in this case, if you look at it as a function of minus t here at fairly small momentum transfers, means that it peaks at around 4.5%. So that's pretty sizable, but it's not huge, right? So if you think back to yesterday, when we talked about statistics that you need if your beam polarization is lower than you would like it to be, right? The figure of merit depends on p squared and only n. The same applies here. If this analyzing power would be larger, we would be able to measure the beam polarization much quicker and much more accurate. So this means that measuring the beam polarization is going to be challenging in some cases because we need good statistics because the analyzing power itself is only 4.5% and maximum. In some cases, it's much smaller, it's only 2% or even less. Okay, and then before we move on to the Rick case, I mentioned this kinematic correlation. So this really at Rick energies where you have a 100 GeV beam or 250 GeV beam and you have a fixed target, you want to measure an elastic scattering, which in itself I find still fascinating every time I look at this. You have this high energy beam and you look at elastic scattering. So the momentum transfer, the kinetic energy of the recoil is really small. It's on the order of a few MeV. And the recoil angle really is very, very close to 90 degrees. So this is 90 minus the polar angle. So it's between 1 and maybe 4, 5, 6 degrees for a recoil energy of 10 MeV. And that's what you try to measure in the polarimeter to determine the beam polarization. So then at Rick, it essentially looks the same as what I showed at COSY for this experiment. So our absolute polarimeter is essentially the same setup as that previous experiment. I don't know if you can see this very well. So the beam pipe goes in this direction. So one of the beams goes into the picture, and then we have this setup here of this polarized target setup, where we again have the hydrogen source, the dissociator, then the magnetic fields and the RF units, and then around the interaction region here where the hydrogen beam goes through the beam pipe, we have the holding field, which in this case only allows us to define a vertical target polarization, which is all we're interested in this case. And then the beam goes down here where we would have the Rabi unit again to measure the target polarization, or another way to do this is to measure the power consumption of the RF unit. And then in this case, the detectors because the energies are so different, really sit pretty much sideways from this beam direction where it goes through the target on the inside of these flanges to the left and the right of the interaction region here. And I should say for Rick, this polarimeter actually uses both beams at the same time. So one of the beams goes in this direction and the other beam goes in this direction. The beams themselves don't overlap, so they're slightly separated on the fixed target. But we're essentially measuring 4 asymmetries at the same time, right? We measure the beam asymmetry from the yellow beam. We measure the target asymmetry from this yellow beam, and then we have the other beam, the blue beam. We measure the beam asymmetry and the target asymmetry. We only compare 2 of each, though. Okay, that's one. So a little more cartoonish here. We have this atomic hydrogen target in red here, which has a certain size. We have the beam that comes in. The scattered proton in this case goes right down the beam pipe. The momentum transfer is really, really small, right? Less than 10 MeV. And the recalled protons then go in the direction of the detectors here. And what we're using are these silicon strip detectors. So this is a more of a 3D attempt of this figure. You have the beam coming here, hitting the target with this 0.7 centimeter, that's full width, half maximum of the density distribution. And then we have these detectors sitting sideways here, about 75 centimeters from the target. And we use these, the silicon strip detectors, they're vertical, and they're vertical so we can measure the scattering angle here. And then the other thing that we do with these detectors is we're essentially using silicon detectors. Usually you use silicon detectors as some sort of tracking device, right? So you want to measure tracks go through. What we do here is, because the energy of the recalled protons is so low, we're essentially abusing them as calorimeters, because even in a 500 micrometer thick silicon detectors, protons with less than 8 MeV are completely stopped. So we can measure the proton energy in the silicon strips themselves, and then we have this one-dimensional reconstruction of the coordinate. As you can see here, we have a combination of a total of 8 panels here, and we use, it's essentially an array of 4 different detectors, because these are doing the same thing and these are doing the same thing and the same on the other side. But what you do is you have one detector that's downstream of the elastic scattering, where the beam from this side hits the target. So that's indicated by this yellow color. And then the other beam would go this way, and the scattering would go downstream here into the blue detectors. So these detectors are actually for the blue measurement. These are for the yellow measurement. And they can also be used to determine background contributions for the respective other beam. But that's a detail that we're probably not going to talk about. This is a picture of the detectors themselves. There's not much else to see in there, I guess. So talking a little more about the measurement itself. So let's start with a simple toy Monte Carlo. So there's really not much in here. It's just a toy Monte Carlo that assumes a certain bunch length, bunch width, and detector resolution, energy resolution. And what you can see here are the basic features of what we're trying to measure. So the silicon strips measure the energy, as I said. They measure the time of flight from the interaction point to the detector. And since the energy of the protons is so small, we can just assume that this is completely non-relativistic, right? So this functional form is really 1 over the time of flight squared. So that's why you see this shape here. And then, as I said, at some energy here, in this case at 7 MeV in this toy Monte Carlo, the protons actually start to punch through the detector slightly. so they don't lose the full energy. So what we measure is less than the energy that they really had. So the real functional form would look like this, but at this point, we don't measure the full energy. So this flips around. And then at this point, our acceptance is at its end. So anything that would have a higher energy would have a scattering angle that's larger than what the detector actually covers. So we use this time of flight information, this function form, as some sort of particle ID. If we had lighter particles, they would sit down here. If we had heavier particles, they would sit up here. So if we could fit this, we know this is a proton. So that's the particle ID. Now we look at the real data, it doesn't look quite as nice. I should say that the energy range is not exactly the same. This one is 0 suppressed, so you would only go down to 1 here. That's why it's not quite as steep. So the functional form itself would be the same, but you can see there's a lot more going on. The resolutions are worse. There's something else here. There's a lot of punch through, and then you can see there's also a lot of other background, and you can see there's a stripe here. That's just from the calibration, but it doesn't look quite as nice. Now, the other thing that we want to use is kinematic correlation, which I said is the 90-degree between the recoil and the scattered particle. This is from a full simulation now, so this is using Pythia, Pythia and some sort of detector simulation, where this is the angle between 90 degrees and the polar angle. So again, the detector sits between 1 and 4.5 degrees here. And you can see the elastic signal here nicely going through. There's some inelastic events here, and then a few scattered particles here. Those actually are photons from really hard QCD events where you don't have the requirement that everything needs to go downstream from the target. And this is mostly inelastic by zero production. But really what you see here is this nice correlation between the recoil energy and the location of the detector, this recoil angle where you have the strips. And that is something you could also see in the data. So if you look at different strips here, this is the one that sits closest to 90 degrees. You see the signal here at low energies. If you go 2 strips up, you see the recoil signal move up to 2 MeV. 2 strips further up, you sit at 3 MeV, and then at the edge of the detector, you go up to 5 MeV. So you can actually use that in the data to identify your elastic signal, and then you use the functional form to do your particle ID to get the elastic recoil proton. Now, if you want to put this all together, as I said, we have these 2 beams here, blue and yellow. We have these different detector setups. We compare these asymmetries. We know the target polarization. So we measure the beam polarizations. If you look at what we had before here, if you look at all this background region, you can also look at an asymmetry that you would measure here, try to interpolate that between or under the signal that you have. You can do the same if you measure an asymmetry here that actually is in the recoil, is in the proton particle range, but it's outside of your elastic range. You can look at this too and try to interpolate this to correct background. And then you can use something that Rick has and also the electron ion collider would have, which is there are some regions in your bunch train where the bunches are empty. That's called the abort gap. And you can use that to see if there's some sort of background that's unrelated to the beam that comes from the other beam, or a background that's just noise. And you can look at this in different ways. One of the ways would be if there's a polarization independent background, and this in first order really means that everything that's unpolarized here might contribute to the asymmetry. So unpolarized background reduces the asymmetry, but it reduces the asymmetry in the same way for the beam and the target, right? Because it's unpolarized. In this ratio, it would fall out. So everything that is not polarization dependent does not dilute my measurement of the beam polarization measurement. Another case is if there's a polarization dependent background, and that might have different reasons. It might be physics or something else. But this polarization dependent background is not necessarily the same for the beam and the target, because that would sit in different kinematic regions. So the polarization dependent background would have to be corrected, but we can actually look at that if we use these abort gaps. And then this is how this looks for a whole year of RIC operations. So for the two beams that we have, we have this thing that's called the fill number, which started counting on day one of RIC operations. So in this case, we're up to 18,000. And you can look at this and you see that the beam polarizations are between 50 and 70% for each of the RIC fills in both beams. You can look at this fill by fill, where you do what I just talked about, or you can try to determine the mean analyzing power for your whole data set, and then use that to determine the beam polarization for each fill in a different way. Look at consistencies or inconsistencies between the two ratios. You find that there's nothing systematic going on if you look at the reduced chi-squared function in this case. So you could think, well, that's all nice, we're done, right? But this really is only one mean polarization that you get for each RIC fill. So it's actually only the first requirement that we had on our list. So what we still need is the bunch profile, the time dependence, and all the other things that we had on the list. So we need to combine this with something else. So this is a good start, and this is our absolute beam polarization. But we need to make sure that we understand the relative features, like we said yesterday. And what we're using for these are what we call the carbon polarimeters, which are ultra-thin fiber targets, which achieve different things. So first of all, they're fast. They're very dense targets, so they have a high interaction rate. So you get a measurement, a relative measurement of about 4% in about half a minute. So that's good because you have a short measurement, but this measurement actually would interfere with the experiment itself. It creates a lot of background, and it would also lead to beam deterioration pretty fast. So you want a fast measurement every few hours, during which time, those 30 seconds or 2 minutes, you switch off your experiment, you measure the polarization, and you go back to your experiment. So you can measure this a few times every few hours. The target is very thin, so you get a way to scan through your beam and measure as a function of the target in the beam what the polarization is. And also because it's fast, you get a very fast way to measure the relative bunch by bunch polarization direction. So how do we do this? So we have these ultra thin carbon ribbons. Ideally, what we would like to have is something that has a size of fractions of a micrometer, on the order of 100 nanometers or maybe even 50 nanometers or less. This is driven. So what you would need to measure the beam dimension is something that's fractions of a millimeter. You want a very thin target because it would have an effect on the beam, and also the recoil. In this case, we measure the recoil carbon from this target. The recoil carbon actually interacts with this thin target, even if it's just a few micrometers. So the energy of what you would measure, what comes out, is going to be very different if the target is 10 micrometers compared to 100 nanometers. So the reason why the dimensions look like this, like a small and thin layer, is because this is an effect of how you can actually produce the targets. There's no way to make them nice and symmetrical right now. So what you use is you evaporate carbon on some sacrificial layer until you have this required thickness, but that also means that you can make it thinner than this, and then you etch away that sacrificial layer. What you ideally would like to have is that the beam hits the target, and this is the most that the recoil particle, would travel through the target to get out into the direction of the detector. If you look at a picture of what this target looks like, it's not easy to really define what's the width and what's the thickness, right? Because this ribbon starts to twist and turn. So in this case, if your detector would be sitting here and you go into the target here, the recoil would have to travel a long way through target to get to the detector. So this would not be a good measurement. If you hit the target this way and the recoil goes out in this direction, it would come out pretty quickly and your measurement would be much better. Unfortunately, you don't really know where you sit with the beam on the location of this target. So you really have to make a measurement and then see what you get out of this. So in terms of the setup of the detectors, it looks pretty much the same as what I showed for the hydrogen jet target. The setup itself is a little smaller because you only need these vacuum chambers. They're about 1 meter long. And then you have this fiber target that would sit in the beam. You have detectors to the left and the right. And in this case, actually you have space to put in other detectors under 45 degrees, which is nice because you can get a handle of the direction of the polarization direction, not just the absolute value. And in this rendering, you can see that the detector boxes, these are the detector boxes, which is where you plug in the cables for the readout. The detectors themselves, again, sit on these flanges directly, and there's the same silicon strip detectors. They're a little closer. They're only 18 centimeters away to make the time of flight just about the same as for the protons, which means that they're slightly smaller, but the relative dimensions are the same. And then we're using these target holders where you can see, I hope you can see there are 6 target holders combined in this one setup, where the target would sit at the front here. And in this photo, you wouldn't be able to see it because they're too thin. And then you can, you're using this motor to move the targets into the beam when you want to use a measurement, or you actually scan the target through the beam when you want. So step 2, the polarization decay. As I said, this is a fast measurement. Takes about 30 seconds to 2 minutes in total for each. And this is just one example from one of the RIC fills that we had. You do one measurement at injection here at 24 GeV. Then you do the ramp up. You do one measurement right before you start your experiment. Then a few hours later, you do another measurement. A few hours after that, you do one more. And then right before you dump the beam, you do one more. You can see each measurement has, I mean, the precision is not outrageously good, but it's good enough to fit this and do this for each fill and see that you get consistent results overall. What you then do is you calculate the mean polarization here from your time dependence, and you use this to normalize it with hydrogen jet. Now, I should maybe mention, we just use a linear approximation. Obviously, this should, on paper, this should be an exponential decay, but if this dp over dt is small enough, we just, in general, just use this linear approximation. So the typical polarization decay over the last 15 years now that we've observed is on the order of 1 or 2% per hour. So it's fairly small. So the normalization with the hydrogen jet target actually uses this the folding of the beam polarization, which is time dependent. For the hydrogen jet, where we have this essentially constant thickness target and time independent, so it's only folded with the intensity of the beam that I'm interested in, which is what I'm doing here. For the experiment, that looks slightly different, right? Because I have an overlap of this beam that I just measured with the other beam, but both of them are now folded into my luminosity. Both intensities are folded into my luminosity. If I measure the single spin asymmetry, it's only one beam polarization. I could be interested in a double spin asymmetry where I would have the time dependence of both beams. So I need to make sure that I have all the information to normalize this with this, but then use this the right way to calculate my polarization in collision. So this is very important, and it's actually a significant difference of the mean polarization that I'm using in the experiment. The other thing is that I can have a beam polarization profile in my bunch. So what the P carbon targets do is they go through the beam and they measure the polarization at each position here. So what they do in the sweep is they determine a mean polarization where I fold the y dependent polarization with my beam intensity as a function of y, and that gives me an x dependence of my profile. I can use a target that goes in this direction and do the sweep in this way, which would be px times ix, and that gives me a profile as a function of y. Fortunately, it turns out that both are about the same for Rick, and they should be the same for EIC also. And then what we do is we need to determine this profile parameter R, which really is just a comparison of the intensity, the width of the intensity distribution, which is sigma I. So that's a Gaussian distribution. And then we assume that this polarization profile is also Gaussian, so that's sigma P. If there's no polarization profile, sigma P will be infinite, right? So the profile parameter would be 0. What we measure, and that's again, has fairly large uncertainties. So even the fit in this single measurement is consistent with 0, but overall, in average over the whole year that we do this, or fractions of the year, we find there's a consistent profile parameter that's not 0. So throughout the store, throughout our measurement, the profile, the bunch polarization profile actually increases. So at the start of the store, the bunch polarization is flat. At the end of the store, it's significantly peaking in the middle. Okay, I mentioned this on the previous slide already, so I could probably be fast on this. This is part of the what I mentioned before, that the scattering of the recoil and the carbon target dilutes my kinematic correlation and the energy resolution or measurement itself, not resolution. And this just mentions how we calibrate the targets. We could talk about this in the afternoon if you want more information about this, I think. One thing that's really important, and it's going to be even more important for EIC, is the target lifetime. As I mentioned, the targets are very thin. The beam is really extreme, high intensities, high energies. And the first thing that you should worry about is that the target just blows up because it heats up too much just by the energy loss of the beam that hits the target. And that's going to be the major problem for the EIC. But what we also observed, and these are real pictures taken by camera in the beam pipe, is if you just come close enough to the beam, if you don't even touch the beam yet, there's a wake field that the bunches carry with them behind them, and this wake field actually induces a charge, a current in the carbon targets. You can see here the beam still is not on the target, and even here the beam is not on the target. You can see this heating up of the targets at the edge, or at the end where we have this holding fork. where this current actually is the largest from the induction of the wake fields. And this is something that caused consternation for a long time because it really leads to a shortened target lifetime and breaking, like the targets really just break off and flap around in the beam pipe. And this engineers were able to mitigate this by introducing these flaps, which picked up more of the wake fields and tried to distribute the currents more around the edges of the target ends. So this was mitigated for RIC. It's going to be a question how successful this is going to be for the EIC.
The size of these images?
This, yeah, I should have said that before when I showed the picture. This is about, what do you think? Maybe a little less than an inch. So it's not large. Yeah, maybe 3/4 of an inch. I would roughly guess right now. Okay. So I think we've covered most of the parts of our requirements, and the last one we really need is the local polarimetry. So at RIC, that's pretty straightforward because in the early RIC days, people found that there was a way to use the primary proton-proton collisions as a means to measure the local polarimetry. That's something that at the EIC will not work. So we need to have a different way to do it there. So what we can do at RIC is when we have PP collisions, we have these 0D. So here's the interaction point where we have the experiment that would be Phoenix or star or whatever. And we have these 0-degree calorimeters, which are intended to measure neutrons that come out of the interaction at 0 degrees. So in this case, this is a small angle where the beam pipe already goes to the side from the outgoing and the incoming beam. So this is really 0 degrees with respect to the beam direction. And it turns out that if you measure the single spin asymmetry of neutrons at this high rapidity range, that they have an asymmetry that is spin or polarization dependent, and this asymmetry is actually larger than what we use in the hydrogen jet target. You can see this peaks at about 8%. This is as a function of the azimuthal angles. You can really nicely fit this, and this is something that has been used at RIC for local polarimetry in the way that during setup you have transverse polarization, right? You measure this asymmetry, and then you switch on your spin rotators and you try to rotate your polarization direction in longitudinal direction. And what you're really trying to do is get rid of this asymmetry. So what you want to measure is 0. If the polarization vector goes in any other direction, it might go sideways, so you peak here. It might only partially rotate, so your asymmetry is smaller. Really what you're trying to do is you try to show this asymmetry is 0. And at the same time, in the polarimeter, you still measure your asymmetry at a different location in the accelerator where it's vertical. So you know there is a polarization, but you don't observe it in the experiment. So you say this is longitudinal now. So that's how this was done at RIC. One interesting thing that people think about for potential future use is a different sort of spin asymmetry of forward-going neutrons, which was observed in Phoenix and also in STAR in 2015, where we have these asymmetries that I just talked about, and we use different colliding beam systems here for the first time. So we originally have polarized PP collisions, and in 2015 we have polarized protons with aluminum and polarized protons colliding with gold. And you can see if you look at those forward neutron asymmetries, they not only switch sign, but they're also much larger. And the nice thing about this technique would be that if you were able to use this for polarimetry, these neutrons are very high energy. so you understand them very well. And they're very good control in terms of measuring and detecting them, as opposed to these low energy protons or carbons that you use, which are, they're essentially stopped in micrometers in your detector, whereas these go through a lot of material, are very resistant to any interaction and things that you would have in front of your detector. So this would be a much more reliable measurement and very advantageous to study other background contributions and smearing effects. Okay, in a few more minutes that I hopefully have, we're going to move from RIC to EIC. So we've seen this. This is the RIC data where we have the time of flight as a function of the recoil energy. This is our signal. Here's the background now, prompt particles that dominate this figure. We try to describe this in Pythia and Geant simulations. It doesn't really look super nice when you compare it, but I thought I would call this a reasonable agreement. Obviously, it's easy to describe this functional form, the punch through edge here, where you have this, and then you have a larger contribution here from background that might be from the target chamber, and other inelastic contributions where you have charged pions and photon conversion that contribute here. Obviously, the description of the detector and the overall setup isn't perfect, but you can see that it has some of those features, right? If we go to the EIC, the picture changes. So here you see the time of flight is at maximum 70, 80 nanoseconds. The bunch spacing is 100. So you have a nice window where you have your time of flight that really fits into your bunch spacing. For the EIC, this goes down to 10. And this is what this would look like. So we take this, we reduce the bunch spacing to 10 nanoseconds, and we put all in one plot. What you want is this red line. That's your elastic recoil. Here it punches through and it turns around this way. Now you want to be able to distinguish all of these lines, right? Because this might have a positive polarization. This might have a negative or positive. This might be negative again, positive, negative. So you really need to be able to say this event was from a bunch where my polarization direction was supposed to be positive. So there's so much overlap here. The punch through really makes this low energy region pretty much unusable. So what you can try with the protons is you can use a second silicon detector layer and try to veto the punch throughs. So you try to get rid of this contribution here. This is on this plot now, and you can see it's cleaned up quite a bit. Distinguish as a function of the energy, you can really distinguish the different bunches where this recoil proton would have come from. You're still reaching a problematic region here at maybe below 2 or 1.5 MeV. Currently, we go down to about 0.8 or 0.6. And this is the region where you have most of your events also. So it would be nice to be able to keep this, but you can see that you can actually get to your polarization measurement for the absolute polarimeter. For the carbon targets, it's going to be a lot more challenging because your recoil energy only goes up to about 1 or 1.2 MeV. If you look at this low energy region, you see this is where your analyzing power is the largest, and large in this case for the carbon recoil means it's only 2%. If you are not able to use this region, your analyzing power is down to sub 1%, and there's actually a zero crossing at one point where you really want to avoid averaging over this energy range because it would average out to zero, right? And also, you can't really use the punch through technique for the carbon recoils because the carbons, even if they have 5 or 10 MeV, since they have a much higher charge, they're still going to be stopped within 10 or 20 microns. And the detector thickness currently at the lowest end would be 300 microns. So that's going to be one of the issues. And the biggest issues for the carbon targets is, even though the bunch intensity per bunch at the EIC is going to be a little smaller than at RIC, the bunch number and the total current in the machine is going to be about a factor of 10 higher. So overall, just the energy loss on the target. So this is a calculation for RIC, where you have the bunch. So the target moves through the beam, and you calculate the beam to the target temperature, which is really just driven by the energy loss, the EDX on the target, and the only way to get rid of the heat is by radiation. And no thermal conductivity, essentially because the target is too thin. You can see that if you move through the target, the temperature rises quickly up to 2000 Celsius. The dashed line here is the sublimation temperature of the carbon targets, at which point they would just blow up. And you see at RIC, you're very close to this limit. If you increase the current, essentially the EDX in the target itself, you find that at EIC, you would exceed this sublimation temperature by quite a bit. And we're currently trying to find a way to either reduce the target size or find a different material that has a higher sublimation or melting point. Okay, the last thing I think I want to mention here, because I've only talked about proton beams, which is really the biggest focus, but for the EIC, we're also talking about polarized light ion beams. Polarized light ion beams in the baseline refer to helium-3 or helions, which should be which are easier to polarize and easier to measure the polarization. If you talk about deuterons, which might be more interesting for the physics, you have a problem because they have a tensor polarization and it's an order of magnitude more complicated. But just talking about the light ion beams, even for helions, it's not so straightforward because number one, what you ideally want to do is to measure the absolute beam polarization is use this elastic scattering, which should be time invariant, right? So we want to make use of this fact that the beam asymmetry and the target asymmetry are the same, which means that we would need to use a polarized helium-3 target. And the other problem that we encounter is that the breakup energy of helium-3 is only 5.5 MeV. So at that low energy, the helium-3 evaporates a proton and you have a deuteron and a proton. So you need to be able to distinguish this breakup, especially for the case where the beam would break up. So what if you measure the recoil in your target, that recoil measurement tells you that it's a helium-3 that you measured, right? With this 1 over the time of flight squared. If the beam breaks up, it's essentially the same as an inelastic pi-0 production in PP, only that your threshold is not 140 MeV, but 5.5. So there's no way that with the detector resolution, you can pick this up in your measurement of the time of flight and the kinematic correlation. So that's illustrated here. So for pi-0 production, and we've also seen this in the simulation, there's a nice separation of this inelastic region from the elastic curve here for the helium-3. They're essentially sitting on top of each other, and you need a very fine granularity that you probably can't get with your detector to get this. The idea is to tag this breakup, which means you measure the proton and the deuteron and taggers downstream where you have so the polarimeter sits here, so that's your measurement, and then you have a magnet here, dipole magnet, which allows you to separate the primary helium beam from the breakups of the deuterium and the proton, and you try to tag these in coincidence with your measurement here to get rid of this inelastic contribution, which would introduce a spin-dependent difference between your target and mean asymmetries. Okay, to summarize this, here's a table. You can look at this offline and think about it some more. It just summarizes what I've been trying to repeat too many times at this point. So we have the different requirements, we have the different potential setups. So what we're mostly thinking about is this polarized hydrogen jet target in combination with carbon or some other fiber target polarimeter, how it addresses the different questions. You can think about using an unpolarized hydrogen jet target, which would allow you to increase the intensity so you could address some of the other issues that would only be available with current polarimeters. And then those forward neutrons in some cases would be very nice to have because they're more resilient, as I said, to some background in physics problems. Now, this is how this currently looks like in people's heads and computers. So we've moved the polarimeters to what's called IR4. So that's the 4 o'clock, excuse me, the 4 o'clock location in the hadron storage ring. So the hadron beam comes in from this direction, and it goes through these dipoles and triplets. And then we have the polarimeter suite here, and I think I haven't said that before. It's super important that this H-jet, the polarized hydrogen jet polarimeter, sits very close to the carbon polarimeters. Especially, there shouldn't be any magnetic fields between the two, because that would mean that we introduce a change of the polarization vector. So if you want to use this to normalize that, we need to make sure that the direction, at least in both locations, is the same, right? So we have the H-jet, the carbon polarimeter set up here, and then we have what I showed on the previous slide, is dipole, which really is part of the EIC accelerator itself. So we're just cannibalizing this or piggybacking on it. And then we need some drift space, about 20 meters. And then we could put hadronic calorimeters, same as the 0-degree calorimeters in these TAGA locations for future helium-3 polarimetry. And then the last one, just to show you some nice picture in this case, is the local polarimetry, in this case for EPIC. Which would be a separate setup. And as you probably all have seen from John's talk and know anyways, space around the interaction region is tight. So we've got the detector, we've got these D0 magnets and other things. We've got the rapid cycling synchrotron, forward and backward detectors, and you have to make sure, you need to make sure that you have space to access your stuff. So we found a space, a location where we could put a fiber target polarimeter, which in this case is just a carbon copy of currently the carbon polarimeters, just a single target setup where you would be able to measure the polarization vector close to the experiment. So that's the idea for right now. And this is just a recap. I don't know if I should go through all of this. We've seen this many times, so I think I'm just going to close with this. And I hope everyone's excited about the EIC coming up. And let me just go, so thank you very much. Let me just go back to your recitation question to point this out so you have the page number. Thank you.
Back on slide 63, and you were talking about the deuteron being much more complicated because it has tensor polarization.
Yes.
Is that because the neutron and proton are aligned that it's spin one, or is it?
Yes. It's the spin one. There are other things that, which complicated a lot for the accelerator, which are the Siberian snakes. And I don't really have the information. I can just give you the statement for Deuteron beams. The strength of the Siberian snakes in the current setup is probably not enough. So preserving the polarization is going to be very challenging, and measuring the polarization at this point, we wouldn't even know how. Okay. Yes, I will be around.
9. So, we're discuss during the discussion.
Yeah, I don't know if the page number is the same on the PDF, but if you look for this thing, it should be right there.
So let's thank Oleg once again. Time, let's do 1 hour and a half for lunch, so perhaps we return 1:15.
Page 9 on the PDF.
Page 9.
Page 9 in PDF.
Thank you.
Let's do it like this. Let's go.